Okay, so we continue the lesson of this matrix powers. So this is actually an important topic, so this is why we spend so much time on it. I want to start from this theorem here. So let us go here. Theorem 120. Let A and B be commuting square matrices of the same order. Then for every non-negative integers m and n, a to the m and b to the n also actually commute. Which is not trivial, of course, because if you have a matrix and you raise it to some power, this would be totally different matrix, okay? And we know that there is no guarantee that the matrix multiplication enjoys the commutativity. So this is the point. Let me tell you what I mean. I mean that if you start with two matrices, A and B, so that you know that they commute. So you know that if they commute, they have to be squared of matrices of the same order, otherwise this cannot happen. So we know that. For example, I want to convince myself that if I raise this one to power 2, and I raise this one, for example, to power 3, in principle, there is no clear connection between A2 and A. You cannot feel, when I calculate A squared without telling you A, if I give you A squared in its final form, you cannot realize this is the square of a given matrix, yes? Because you just see the matrix in front of you. And B cubed. My goal, for example, is to show that this is also the case. This is the content of that theorem, not only for 2 or 3, for any numbers that you want, yes? But of course, non-negative integers. So this we know, this we want to show. Of course, this is not the proof, because the proof you need to do it for all integers. I am just choosing it for 2 and 3, but it will capture the essence. If you want, you can also go and then prove it precisely. And I will tell you how to do it precisely. That's a good exercise in mathematical induction as well. So how can I prove that? For example, I want to show that this one is equal to that one. So for example, in this case, if you want to do it case by case, you can start from this one. There is only one way for me, is just to write A times A, and then B times B times B, yes? So then you have to use associativity in an efficient way, but here you also have commutativity of A and B, okay, only. So what can I do? For example, I can write, because I want to move all these B's to the other side somehow. So is that possible? So I would say that A, and then I keep them like this, and then I have B, B. So you see, I have used associativity to regroup these two together, but now I can switch them. So this becomes A, and then it becomes BA, and then I have BB. Okay, then what can I do, for example? I can put the pair of brackets around these two. I don't know which one is the most efficient way to do it, but I put them here, and then I have A, B, B, and then I replace them, for example, it becomes BA, A, and B, B, something like this. So I don't want to go through this process anyway. I'm not saying this is the most efficient way to do it or not, but hopefully you see that again, I can switch these two and switch them, and I can move all B's to the left and all A's to the right. Yeah, is that clear, or do you want me to continue? For example, here, I can actually switch these two once more. So this becomes BA, and then I have BA, then I have B. I can switch these two again. So this becomes B, B, A, B. I don't know, I can switch these two again. So this becomes B, B, A, B, A. And then finally I can switch these two, yes? This becomes B, 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 A, and this is B3A squared. I'm not saying that I did it very efficiently. Might be you can find it in lower number of moves, yes, less number of moves, but this is possible. So I'm using associativity and the commutativity to be able to flip these two finally. Yes? So, but if you want to prove it in general, what do? You prove it like this. You would say that if you tell me A and B commute, then it means that this is the real proof. Then it means that AB is equal to BA. So you tell me this is true. But then I will prove that A to power n times B is B times A to power n. Only, so what I am doing, I am keeping B the same, but I am raising A to some power n. I want to convince you first that if this is true, that is also true for any n. This I can use mathematical induction. Yes, how? I would say that my goal is to prove this. So let me call it Pn. This is ANB, this is BAN. So the first thing that I do, I will check the validity of P1, which is A to power 1B is equal to BA to power 1. True or false? It's true because this is my assumption. So that's true. Because A to power 1 is just A. Now assume that P of K is true. It means that A to power KB is assumed to be assumed to be true. And then I want to prove that P of K plus 1 is also true. So I want to show that A to power K plus 1B is equal to B A K plus 1 to be proven. Yes? This is what I want to prove. So what can I do? I want to prove an identity. Might be the most natural ways to start from the left-hand side of what I want to show and try to manipulate it and try to reach to the other side. Of course, I have to use probably my assumptions. So if I start from the left-hand side of this one, okay, can you tell me what to do? These are extremely standard things. I mean, in a matter of seconds, you need to know where to start from. So what should I do here? I write the left-hand side, then seconds in your reference frame is different from my seconds, yes? Yes?
What if you separate A to the power K?
Yeah, exactly. That's I have, because I want to use, this is the trick. In this, I want to do it in a way that I can use this. So in this case, I have A to power K. So this might motivate me to get rid of one of these A's. Instead of A to power K plus 1, we had this before, that I can write it as A times A to the power of K, and then times B. So what I do, in principle, I have to put a pair of brackets around that. Instead of A to power K plus 1, I wrote A times A to the power of K. But because of associativity, I can replace the pair of brackets around the second pair. Yes? But according to my assumption, AKB is BA to the K. So instead of AKB, what can I write? Yes? And then I use associativity once more to remove the pair of brackets around the second pair and put them around the first pair. And then I can flip these two because that was given in the beginning of the problem. So AB and BA commute. So I can write BA. And then after that, I have A to the power of K. Again, I have to use associativity. And then this is done. Yes? So I was able to use mathematical induction with a few number of associativity properties, and of course using this at some point and using my assumption at some point to prove that the left-hand side is indeed equal to the right-hand side. So, but if I ask you what I proved, you will tell me that you only raised one of them to some power. But then the next step is actually the same thing. Yes, this tells you that if I give you a pair of matrices that are commuting, you can keep one of them fixed and raise one of them to any power that you like. Still they commute. Okay? Okay. Now let us see what happens. I gave you a pair, you conclude this one. But forget about the original pair. Now look at this one. I have a pair of new matrices. One of them is A to power n, one of them is B. This idea tells you that you can keep one of them the same and raise the other one to any power that you like. Yes? So I will do the same thing. I will keep an the same, but I raise this one to any power that I like. Yes? So this means that from here I can conclude here, from here I can conclude this. So it means that if I have a pair of commuting matrices, it's interesting to know that it doesn't matter if you raise one of them to any power, for example 2, the other one to any other power, or even the same power, then the resulting matrices are still commuting. Okay? That is one thing, that's the content of this theorem. Now let us go back. Any questions here? Let us go to this theorem. So do you remember we talked a little bit about this formula? Do you remember this formula was not in general valid? This is valid in numbers. So that's also one deviation from number algebra. Yes. So let us go back to the board. So here, if I have numbers, for example, a, b to power 3, if they are numbers, then I can write a to the 3, b to the 3. But if they are matrices, there is no guarantee that this is the case. Why is that? Because if you go through the proof of this for numbers, you see that you have to use commutativity, which is not the case in general for matrices. So here, if I want to prove this for you in Math 1C, for example, I would write it 3 times. And then I can interchange A and B. I can change A and B's because I know commutativity is valid. So then I will have all A's on the left side, all B's on the right side, then I will have A to power 3, B to power 3. So at least you have some right to be suspicious about that this might not be true for the matrices because we do not have commutativity. So this is also another deviation from number algebra. So I want you to make sure that you understand that. Okay, so, but this tells you under what condition this is valid. Of course, you could guess. Under what condition? So if I want to use this, AB to the power of n is equal AN, BN, under one condition this is true, and that is A and B are commuting matrices. So let us prove this one, okay? So I will also prove this using mathematical induction. So let me call it Pn. And then I will check the truth of P of 1. So this becomes AB to the power of 1 is equal to A to power 1, B to power 1. But this is true, yes? That is true. I will assume that P of K is true. AB to power K is equal to AK, BK. Okay? So I want to test your understanding now. So if I want to prove P of K plus 1, so this is assumed to be true, yes? I want to prove that AB to the power of K plus 1 is equal to A to the power of K plus 1, B to the power of K plus 1. Yes, that's my goal to be proven. So let me take this slide off. Okay, so how should I prove this? Again, as usual, you want to prove an identity. One standard way is, if possible, to start from the left-hand side and try to simplify this to reach to the other side. Okay, so how should I do that? Can you help me to do this? So your goal is to start from here and go to this side. Of course, you can use this. By the way, I forgot to write that because it is in the slides. A and B are commuting. If A and B are not commuting, I cannot conclude this. Okay, so I have 2 assumptions in my hand. One of them is the standard, is the one given in the theorem itself, and the other one is the assumption in the induction. Yes? So how should I calculate? How should I continue? Yes?
Well, you can write AB to the power of K plus 1 as AB to the power of K times AB.
Yes. This is one. Of course, you can also write it the other way around. Which one is superior, we don't know. Let us start with one of them. Yes? In principle, you could write AB times AB to the power of K, but let us just stick with this one. If it doesn't work and we realize the other way around will work, then we have to cross it over and be patient and go back and do it all over again. So what happens here? So AB to the K, what can I use now? I have something in my hand. This one is assumed to be true, so I can use this. Okay, so I would say that this is A to the power of K, B to the power of K, and then I have AB. Now I want to tell me what to do now, from now on. Do you have any opinions now?
You can open up the brackets.
Okay, so assume that the brackets are now opened. Okay, then what? Yes, Sarah?
Can you regroup them
How?
so that it's AK and then BK and A are together in the bracket?
So you want to put all three of them in one group?
No, BK and A together.
Okay, BK and A in the middle together
Yes.
without changing them, and then AK and then B. Okay, then what? Can you continue yourself? Yeah, that's correct. But then what? Yes, Robert?
According to the last one.
According to the last one. That's important, okay? So if I want to prove this, I had to prove that one at first. Yes? So this tells you that if I have two commuting matrices, if you decide to raise one of them to some power and keep the same for the other one, they are still commuting. Okay, now I have the same situation here. I know that AB and AB is equal to BA. I can keep B the same according to the last theorem. This is not here, that is there. According to the last theorem, I hope that you agree with me, this is also true. Okay? So you see here, I kept B the same, and I decided to raise the A part to some power that I wanted. I chose to be K. So this arrow is not this problem, it's the previous problem. Is that clear? But I can use it because I have already shown that that is true. So then what I do, I will say that, okay, I will continue. Instead of that one, I can write AK and then ABK and then B. And then everything becomes clear, yes? Then again, I regroup them back in this way, A to the K, A, and then B to the K, B. But this means that this is equal to A to the power of K plus 1, B to the power of K plus 1, and that is the right-hand side. Yes? Okay, so that is also the proof of this theorem. Any questions? By the way, sooner or later, I will give you some descriptive questions in quizzes, because my feeling is that you are not doing properly this. Are you reading? Are you doing exercises or not? It's clearly not that much, yes? Yeah, so exams are probably the only way that I can push you to work, yes? But anyway, I hope that you are solving these exercises. Okay, so sooner or later, I will give you some quizzes that you have to write it down and send it to me, okay? Okay, now let us go back to slides here. This I want you to understand quite well, okay? So which of the following equalities is in general true? Okay, so it means that you can rely on them. All matrices are assumed to be square matrices of the same order. Okay, now I'm asking you, do you agree with this algebra? I have done some algebra here. A to the 3 times a plus b to the 3, I have written it as a squared plus ab totally to power 3. This is an algebra that I have done. Do you think this is a valid way of doing this algebra or not? So do you know why I'm asking this question? Let me ask you this question. If I give you numbers, a to the power of 3, a plus b to the power of 3, and then I write this, by the way, this is a Math 1C problem, yes? So tell me, is that true or false? If a and b are just numbers. So first you need to tell me why this is true if it is. Is it true or false? I have to kill myself. Is it true or false? Yes.
It's true.
It's true, yes. Because why is it true? But this is, by the way, Math 1C problem. You shouldn't have that problem. It's just a matter of seconds. You should be able to understand that, yes? What is it, true or false? It is true, and that is this theorem. If I have a to power 3, b to power 3, what can I write? I can write ab to the power of 3. This is exactly the same problem again. You know it, but you cannot use it. This is not any teacher can teach you. You need to teach it yourself because you have the knowledge, but some reason you don't use it. This you need to say, aha, next time I will use it, I promise myself. I don't know, you need to do something, yes? Okay, so this is correct. Why? Because now if I give the role of capital A to this, and I give the role of the capital B to this, then what do you see? You see A, capital A cubed times capital B cubed. But you just told me I am allowed to put a power of 3 up there and then multiply capital A, which in this case is little a, by capital B, which in this case is A plus B. But then what happens here? This becomes A squared plus AB to the power of 3. So yes, what I have written here on the board is completely valid if A and B are numbers. But I am just writing the matrix version of the same thing. I'm asking you A to the power of 3, A plus B to the power of 3. Can I be in general sure about this, that this is also the same thing, similar thing? Now I'm asking you, evaluate this. Is it correct or not necessarily? And then just try to talk a little bit about that. Yes, please.
I would say it works.
It works, okay. Any other opinions? Okay, Rocco, when you say it works, you need to defend yourself now.
So again, I don't know the terms for the properties or anything, but the question is, if you have that A times A plus B, if you can distribute, I think it's a distributivity when you multiply.
No, before distributivity, you need something.
There's
You're
something.
jumping ahead. Yes, that part is called distributivity.
Yeah.
Yes.
Which we
But-
can do with matrices.
Yes,
right?
in matrices, distributivity we do not lose, okay? But before that, I just told you, I am
Oh, we
using
don't-
this.
That's valid.
Yes, this is not valid in general in matrices. Do you agree? So if you want to write this, if A and B are pure numbers, don't worry, you can just always write it if you want to. But if A and B are matrices and still you want to use it, you have to check something before using it. What do you need to check? They have to commute. Yes? If you don't check that, you cannot use it. So it means that yes, if I can go from here to here, then of course I can continue, because from here to here I'm just using distributivity. And distributivity is preserved in matrices. But can I just go the first step? Can I do that? Can I write A to the power of 3, AB? Let me write it again. This, if I can write it like this, then of course Rocco is correct. I can still distribute, then it becomes A squared AB. Okay, so this is 100% correct. This is 100% correct, but there is this one you need to make sure that you can pass through this equality sign. How can I check that? How can I check that if I can do it? The matrices involved in the formula should be commuting. The matrices involved on the one hand is A, on the other hand is A plus B. So I have to go a scratch work, or I don't know, I have to convince myself if this is true. If this is true, yes, this is also valid, then I am done. But if I do not have any reason to believe in it, then it means that I cannot use it. So do you think this is correct or not? Let us check. Distributivity is A squared plus AB. Distributivity here is what? Can you tell me? A what?
A squared plus B.
Plus BA. Are these two guaranteed to be the same? No. A squared are the same, but there is no guarantee that AB and BA are the same because it is not mentioned in the problem. So this algebra, I am not allowed to use it. Okay, so I want you to understand these things. Is that clear? Now you have experience, hopefully you can answer the second and the third one. So let us go back to slides. Okay, I want you to think, because I want to give you a little bit of time to think about number 2, number 3, and then defend yourself. Exactly. You start from the beginning and be successful at the very end, okay? I want to wait a little bit for you. Okay, so let us work on this one first. I want to know your opinion about this, if it is true or false. If it is false, tell me why. If it is true, why, okay? So, okay, tell me, I have written it here on the board. Is it true or false? Or it is not, yeah.
It's true.
It's true, okay. So can you defend yourself?
Yes. We do. We can try it.
I wrote something wrong here. Yes, sorry. Let me fix it first. I forgot to write 4 here. Yes, now.
We can try to see if commutativity is preserved in the same way as we tested it.
For which matrices can you name them?
It's A times 2i.
Yeah, this matrix
Um,
and this matrix. If they commute, then I can use this rule of this box to power n times circle to power n is box circle to power n. If box and circle commute, then I can use that. So I have to convince myself this is that you are saying this is true, yes? So let us check. So first, to understand this, I take this one, 2i minus a. By the way, the reason that you are thinking about this, of course, now I am teaching this, you are observant about this idea. But you need to teach yourself in a way that in the future study, some way you want to use it, you should be able to use it. Okay? So that is a harder task. Why do you think that this is coming to your mind? This comes to your mind if your number algebra is good enough. If your number algebra is good enough, you compare it immediately in your head with this situation. And then you know that if I multiply a in, this becomes exactly this combination. So because your number algebra is good, then you understand what to do with this one. Then when you reach to this one, you'll understand that can I use this fact, then I will come here. Otherwise, there is no way that you can understand that. So now you calculate this, and you also calculate this to convince yourself that they are the same. So are they? Let me multiply. A times 2i, what's the answer? Is 2a. A times a is minus a squared. But now let me multiply from the right side. A times 2i, but from the right hand, it means 2i a. What's the answer again? 2a. But a times minus a, the answer is again minus a squared. So in this case, this is correct, that a times this is equal this times a. So then I can use this rule. Okay, so I would say that since a and 2i minus a commute, therefore okay, what can I write? I can say that the left hand side is equal to a times 2i minus a to power 4. This therefore is not a correct sentence. Since a and this commute, just this, yes? And then you can use distributivity. So this becomes 2a minus a squared to the power of 4, and that is the right answer. So in this case, that's correct. What about this one? Any questions here? Is that clear? Okay, what about this one? True or false? Yes?
True.
It's true. So how can you defend yourself now?
The same way that we did in the last problem.
But how do you solve this power of 8 and power of 5?
Oh, you can just split them up so then.
Exactly. So what you do first, you need to let me just start from the left hand side here for this one. So I will split it, as you said, a to the power of what I need, a to the power of 3 times a to the power of 5 instead of a to the power 8. The motivation is that I have a power of 5 here. So in some sense, if I want to use that theorem, these powers should be the same. Okay, so then I would write it this one. This is 2a squared, and then I have plus a cubed and plus I, and then to power 5. Okay, this is always valid. 100% it's valid. But I want to use this idea for these two powers of 5. I cannot use it unless I can convince myself the matrices involved are commuting. Can you name the matrices involved here? One of them is?
The identity matrix.
No.
How do you mean it?
I mean, if you want to use this, you need to convince yourself that the box and the circle are commuting. What is playing the role of the box? What's playing the role of the circle?
It's A and
Yes.
2A.
A is playing, for example, the role of the box. Yes. And this one is playing the role of the circle. So you want to use this idea, but so then you have to stop and convince yourself that you really can use this. How? By going and asking yourself, is it true that A times this involved matrix, 2A squared, this and that, is it really equal to the other way around? So let us just save some time. Just multiply it right away. It becomes 2A cubed, and then plus a to the power of 4 plus a. I hope that you agree it doesn't matter here if I multiply it the other way around, yes? So if I multiply it from the other side, again, I will get the same answer. Yes? So these two are the same. When they are the same, I can use this rule. So I keep a to the power of 3 here as before, and then I put the power of 5, and then I multiply a by 2a squared plus a to the power of 3 plus I, and then what happens? This becomes a to the power of 3, and then I multiply it in. So this is valid algebra. Yes? Is that clear? Good. Let me also finalize today's lesson by just this last remark. This is very important, by the way. I'm just trying to teach you, are algebraic identities also valid when it comes to matrices? Okay, so let me just go back to the board here. So, what do I mean? For example, if I give you numbers a plus b to power 2, you can write a squared plus 2ab plus b squared. It is very useful if I can use the same identities with matrices, because I can save a lot of time, yes? So my question is that, do you think that in general, I can use this for matrices as well? This is always true, of course, if a and b are numbers. Now assume that a and b are square matrices of the same order, so that I do not have any problems with addition, I do not have any problems with the squaring. Assume that everything is okay. But do you still think that this might be valid, or there is a good reason to doubt about it? Because if we can write this is, I hope that you agree, this is very handy, because I can use all identities that I had in algebra here. Now my question is that, do we have a good reason to doubt about the truth of this? Yes?
Because no.
Yes or no first? Do you doubt it or not?
I don't.
Okay, why?
Because it can't be sure that A and B are commuting.
So how is that involved here? Because why do you think this depends on commutativity? You are right, it depends to the commutativity. But because?
We're writing a simplified form, like a final form, but we go through all the steps to see if there is.
Exactly. So if I start from the left-hand side and try to prove it, then I will see that there is a problem. So why? Because when I write this to the power of 2, for the time being, you cannot trust this because we do not have it in matrices. So there's only one way to calculate this. What is that way? To write it 2 times, because distributivity is still valid. So I can distribute it now. A times A is a squared. A times b is ab, and then I go here, I have to write b times a, not a times b. In numbers, it doesn't matter. Yes, and then b times b is b squared. Now the point is that, can I, like numbers, collect them and write 2ab? No, because there is no guarantee that ab and ba are equal. So that is exactly the problem. Of course, I didn't refute it. If you want to refute, if I write like this in the exam and I say, so this is not valid, what do you say? You get 0 points. Yes? Why? So assume that this is the exam. I ask you to prove or disprove. You've correctly realized this is not right, and write this and try to write stories for me. Yes, we know that AB is not equal to BA, so I can, okay, well, but this is 0 points. Why is that? Yes, Alexander?
Well, it might be true in certain cases if AB is equal to BA, for instance, so they commute.
Okay, so what is the logic? So what is the correct logic behind that? So if I give you this in the exam and I ask you, do you think this is true or false? If it is true, prove it. If it is false, you cannot say this argument shows that this is 100% false. Do you understand what I mean? Because, I don't know, someone might say that, okay, how do you know that? Of course, we know that in general AB and BA are not commuting, but how do you know that this will not? They can make stories, you know. Yes, they can make, okay, how do you know that this will not affect there, and then make them commute or something like that? So if you want to disprove something, this is some way to convince yourself that might be 90% this is not correct. But then
You need to give a counterexample.
you need to give a counterexample. And in this case, cooking up a counterexample is not hard. You just randomly pick two matrices. Most of the time they do not commute. I mean, if you just pick two matrices that do not commute and calculate the left-hand side, calculate the right-hand side, you see that they are different. So this means that then this is disproved. Okay, but this is the source of the error. Okay? So do not use them blindly. So let me cross them over. It is not true in general. But of course, now you understand when they are true. Yes?
A and B are commuting.
Yes, if the matrices involved are commuting. So if the matrices involved are commuting, either it is given you directly in the problem or based on your knowledge. For example, if I give you D1 and D2 are two diagonal matrices of the same order, and I want to add it to power 2. Can I use this identity now for these two matrices D1 and D2? These are diagonal matrices of the same order, yes?
Yes, you can use it.
You can use it. Because that was one class. I told you that you need to remember these things in matrix theory. One big class of commuting matrices are diagonal matrices. So it doesn't matter, it doesn't matter in which order I multiply them. Diagonal matrices of the same order always commute. So then I am on the safe side to use this. And it is better to use it because it is faster. Is that clear? Okay. So either they have to mention that these two matrices are commuting, or you need to investigate that, yes, the matrices involved, I see they are commuting, so I can use it. Okay? So for example, can you tell me, can I write this? A plus I, 2I, okay? And then I want to square it. Can I just write a squared 2 times the first one times the second one plus the second one squared? Can I write this? Yes?
Because IA.
Can I?
You can write.
Yes. Because?
IA equals A and AI equals A. So that means.
Yes, you are right, but 99% right. You wrote A and I. I need to
AI,
check
yeah.
A, 2I, yes?
Yeah.
And 2IA. Are they the same? Yes, because A times 2 times I is just 2A. 2I times A is also 2A. So this matrix can play the role of B, this matrix can play the role of A, of course, but we also know in this particular case they commute. So when they commute, I can use this algebraic identity. I would say the first one to power 2, 2 times the first one times the second one, Yes, but 2 times 2 is 4, a times I is a, and the second one to power 2, which means this number to power 2, this matrix to power 2. But what is I to power 2? Is I itself. So that's why I have written I at the end. So is that clear? So this is the end of today's lesson. And this, if I go back to slides, so this remark, I have talked about this identity. Yeah, I want to make it a little more complicated, okay? So here, can I use this identity for this case?
Yes.
Yes, because the one matrix is A, which I don't know anything about, but another matrix is 3 times the identity matrix. I know that they are commuting, so I can safely use the algebra. Yes. Okay, I want to keep it here because I want to give this as your problems to think about. I will start with solving these problems next time. Okay, so the lesson is finished here. Any questions? No? Thank you.